Okay, so this session, okay, let's just briefly overview what we intend to cover over the long run again. Everything in gray is stuff we've already done. Stuff in white is what we'll do today. The yellow one, distortion, we'll just start touching on it today because there's a lot more to say on it. And then the rest, meshing strategies, is still stuff that's to come. Okay. If I look at order of elements and the accuracy and computational cost, they are extremely strongly linked together, which is why then there's maybe because we need to get to numbers to try and estimate which elements are how expensive in terms of solving for a given level of accuracy. Okay, so if we look at the typical finite element analysis process, the three main portions of work that's being done in the background is setting up the stiffness matrix, solving it, and then back substituting to get to the stresses. Usage for the assembly matrix, the stiffness matrix assembly, it's proportional mainly to the number of nodes that you have in your model. Effectively, we're solving over every one of the elements, find its contribution to a specific node and add that stiffness to that node. Now, it's slightly higher than just proportional to number of nodes, simply because the matrix is supposedly square, was not quite square. It's a matrix with a lot of zeros and the zeros are not stored. So effectively, it's a kind of a banded matrix. If I look at the time to solve, is proportional to the number of elements, obviously. So more elements takes longer to set up that matrix, but also how many nodes for each element, because every one of the nodes need to be added. And in addition, the number of integration points per element, because each of those integration points play a role at every one of the nodes. So it becomes more expensive to the information point for every node to the element, which is then added to the global stiffness matrix. When we solve this equation, the memory usage for this part is again proportional to the number of nodes, but now to the power m, and that m power is somewhere between 1 and 2. It's definitely greater than 1. If the matrix was a dense matrix, then the power would have been to the second power, which means it's a full square matrix that in reality full 1.2, 1.3, depending on model size. For larger models, that M coefficient moves down closer towards 1. Smaller models, they tend to move closer towards 2. If I look at the time to solve, I again have a number of nodes to the power of n, but n is now slightly different to the m coefficient. Again, we need to subtract rows from other rows. And since there's more rows and more columns, it becomes more expensive, obviously. So it's effectively, if I double the matrix size or double the model size, it's more than double the time and more than double the amount of memory needed for the stiffness matrix. And then back substitution is again similar to the stiffness matrix assembly, and the same for the time as well, similar to this. What's obvious here is that the number of nodes and to some extent the complexity of the elements play a significant role in this. So when we compare two models, one of the most important bits, if we compare shells to shells, is simply to look at the number of nodes. Same for solids to solids. You can't do the same for shells to solids because they have different number of degrees of freedom per node, but it'll be a very similar process. Okay, so let's try and determine how many nodes we expect for every element that we have in a mesh. If I have, argument's sake, 1,000 nodes, should I have? Okay, so we can estimate this from the number of elements, the number of nodes each element adds, but also how many elements share one of the nodes. So it's easier if you look at an example. Okay, so if you look at the image, there's a first order quad mesh, and if I look at any element, you'll see there's 4 nodes, kind of obvious, but every one of those nodes is shared by 4 elements again. So if you divide the 4 nodes per element by the 4 elements that share the node, I get to 1 node per element. So this means if I have 1,000 elements, I expect to have close to 1,000 nodes. The reason it's not exactly 1,000 is twofold. The first one is when I get to the edges, that node is now shared only by 2 elements instead of 4, and getting to the corner, that node is not shared by anything. So those add a little bit. So it's usually of the order of about 10% more. The second reason is this is for a perfect mesh. In other words, perfect 90-degree angle quad elements. The moment we have a transition, we'll have, in some cases, more, in some cases, coming together. The way close to 1 node. If I look at the second order quad mesh, in this case, we have 8 nodes. So if you quickly think about it, it seems like it should be, well, double the number of nodes per element, but it's not. So let's start again. Every corner node is again shared by 4, and there's 4 corner nodes. So every corner node effectively adds 1 node per element, simply because there's 4 nodes per element shared by 4 elements. If I look at the mid nodes, though, there's an additional 4, but they're only shared by 2 elements every time, which means every one of the mid nodes add 2 additional nodes for that element. So the total effectively for this would be 3 nodes per element. Okay, so the normal quad 8 is actually not a full second order element. In theory, we'd need an additional node in the center, and that node is not shared, so that would get us back to 4 nodes per element if we use such an element. So in other words, a quad 9. If we then split that back to first order elements, but use the same number of nodes, we're back to 1 node per element. So just a circular check to see that we end up with the same initial results. Okay. Now, if I do the same for a lot more element types, if I look at first order tri-elements, we have half of the number of nodes than we have elements in a given mesh. And the reason for that is we've got a 60-degree angle is the ideal angle for it. That means the node is shared by elements, but the element itself adds 3. So it's 3 nodes divided by 6, 0.5. Quad elements, we already know it's about 1. For the second order tri, we can do the same for the mid nodes, and there's 3 additional mid nodes, but each only shared by 2. So that's 1.5 additional nodes per element, and we add the corner node, same as the first order, so we end up with 2. Same for the second order quad, which we've already done. Now we can do the same for solid elements. For the first order tet elements, it's about a quarter the number of nodes than the number of elements. First order hexes, again, we're comparing this to the first order hex. And for second order tets, I'll get to that number why it's a bit more approximate in a moment. And then lastly, for the second order hex elements, we've got about 4 times the number of nodes than we have if that same element was a first order hex. Okay, now the reason for this complex thing is the perfect shape for a tet element is when every one of its faces has got 60-degree angles for every corner. Unfortunately, it's impossible to fill a volume with such elements. So if you look at the, let me just temporarily switch to a model that I've built. So this, these lines represent the top part of the perfect triangle. If I look at the angle between these two, that angle is not 60 degrees, it's 70.53 degrees. And the problem is 360 degrees divided by 70.53 is 5.1 elements that we need in that direction. And it's impossible to have 5.1. In reality, what we'll have is, depending on the measure, it may either squash or expand it a bit. So in some regions, we may have slightly more, in some regions, slightly less than that 5 elements. So if we, in theory, could have had 5.1, it would have gotten to that 1.7, I think. 1.65 is closer to typical measures that I've tested it on. Okay, so the second one is if I have a mesh with a certain element edge length. So if I look at the, let's say a quad of an edge length of L, then the area of that element is L squared. If I try to calculate the area of a triangle, it's 0.86, which is the height times 0.5 times, and then the length times, well, height. So effectively we end up that one tri-element with the same edge length as the quad only has 43.3% of the area of this element. Okay, so if I take the ratio, then is I'll end up with, if I mesh it with the same, well, the same edge length, same surface, and I try and get to close to 60-degree angle tris, which is the most accurate, I'll need 2.31 times the number of tri elements than I need quad elements. So this combined with the number of nodes per element will tell me how many nodes I'll have for a given edge length. If I have different meshes, same length of element, how they compare in terms of number of nodes. We can do the same for a solid element. So the volume of a X element is a length to the third power. The volume of a TET is a third times that base area, which is the same as that number that we get there, multiplied by the height. And this is something I got from that pattern model that I've just shown you. So there I get to the volume for a TET element with the same length as a X is only 11.8% of the volume of the X. So that means to fill a certain volume with the same edge length and assuming close to perfect elements, we'll need about 8.5 times as many TET elements as we need X elements. Now we can do this for more element types. And we can now compare it also. So I combine the previous two. So the one was the number of nodes per element in a mesh, and the other one is the number of elements that you need to replace, in this case, a quad 4. Okay, so if I go from a quad 4 to a tri 3, I need 2.31 times as many elements, but every element has about half a node. So if I multiply that, I get to this 1.16. So in this case, with the same edge length, I expect to have 16% more nodes for that mesh than this one. If I go to the tri 6, instead of that number, it's instead of times half, it becomes times 2, which is what we've previously determined the number of nodes per element for a tri 6. And for a quad 8, it's just 3. It's the same shape, so it's simply how many nodes per element we have. Okay, so that says if I use the same edge length and I get, argument's sake, 1,000 nodes with a quad 4, I'll get 1,116 about of tris 3s, or 4,620 or 3,000 of these. Okay, now if you look at accuracy, this mesh, even though it has more nodes, has a lot less accuracy. It's a lot less accurate model than the quad 4 model will be. So effectively, that's a really bad trade-off. We'll talk about that briefly later, but if I go from this to this, for the same edge length, this mesh is very similar in accuracy to this. So my runtime and my memory usage will be at least 4.5 times more for a tri 6 mesh than a quad 4 for the same accuracy. The quad 8 is slightly different. This is significantly more accurate. So we may get to the point where this is actually worth it. Good. So let's do the same for X8 mesh. So again, everything is relative to this. If I look at the TET4, the number of use again the same edge length for the mesh is slightly more than double. And I get it from the volume ratio times how many nodes per element. And the same for the TET10, so it's that same ratio, but now we have more nodes per element. And I've in this case used a lower number. 1.7 is also a possibility, so then it will be slightly higher even. So that said, and this is based on experience, what I found is these two for the same edge length give very similar accuracy answers. Some cases the TET10 looks better, some cases the X8 looks better. But the expense of switching from X8 to TET10 means we'll end up with about 14 times as many nodes. So it's a lot more. If I go from a X8 to X20, it's 4 times the number of nodes, which is a lot more palatable than 14 times. Okay, so if we compare relative accuracy now for different elements. So we measure surface with let's say a length of arguments like 1 millimeter, and I use different first and second order elements. A quad 4 mesh is much more accurate than a tri 3 mesh. A tri 6 and a quad 4 is very similar in accuracy. There's certain things the tri 6 does better and others that the quad 4 does better. If I look at a quad 8, it's significantly more accurate than these two, but again, it needs more nodes for that same mesh. If I do the same for the solid elements, X8 is a lot more accurate. Sorry, not 30. Let me fix that. Okay, so the X8 is a lot more accurate than this. Again, a TET10 and X8 has similar accuracy, and once we get to X20, similar to a quad 8 versus a quad 4, this is a significant improvement from there. From these to that one. Okay, so it isn't quite as perfect as it sounds. There are specific complications for second order elements, but that's something we'll actually have to discuss somewhat today and then spend more time on a separate session. Okay, so let's try and summarize all of what we've done up to now, because it may not have been clear. If you combine this and keep on going back to the numbers, it may make a bit more sense. So if I compare for shell elements which one to use, there's no reason to use a tri 3 or even a tri 6 mesh if you're only running a shell mesh. If you run mixed solid shell elements, there's different reasons why you may want to use some of those. The reason we only use quad 4 and quad 8 is a quad 4 is more efficient than a tri 3 and has less nodes, and a quad 8 is more efficient than a tri 6 and has less nodes. But it's really easy to mesh either of these. So there's no reason to mesh with a tri 3 or a tri 6 mesh. It doesn't mean your mesh is not allowed to have 1 or 2 of them in. So I can sometimes have a quad 4 mesh that'll have a couple of tri 3s in areas where the quad 4 would be really badly collapsed. The same goes for the quad 8. But dominantly the mesh should be one of these two. Now if I compare these two though, if I double the length, so I use, let's say this is 1 millimeter elements and this is 2 millimeter elements, I'll have a quarter of the elements for the quads. But this mesh accuracy will be very similar to this one if the mesh is perfect. By perfect, I mean 90-degree angles everywhere. Distortion confuses that a little bit. In addition to that, so that double the mesh size, since it has very similar accuracy, the advantage is it'll only have 3/4 of the nodes. So it's slightly less nodes, let's say 70 or 75% of the nodes, and a very similar accuracy. We may need to mesh slightly finer, so it's not perfectly that ratio. We may get to the point where they're actually, for the same number of nodes, it's about the same accuracy. Tri 3 and Tri 6 is always more expensive than quad 4 or quad 8 if we look at the same accuracy. But since auto meshing is easy, if whether we mesh with tri or quads, there's exactly zero reason to waste time and effort on a Tri 3 and a Tri 6. When we look at solids, it's unfortunately a bit more complex. So the only choice here would be the X8 or X20 and the TET10. Now there's penta elements and pyramid elements and so on. In very specific circumstances, they're okay. The problem with those is in some directions they behave like a TET10, in other directions like a X8. So it's not somewhere in between. It's in some directions great, in other directions horrible. So that's why, again, I don't explicitly mention them. Again, it doesn't mean that you can't have a couple of them somewhere to help the mesh get better connected or something. Okay, now if I look at these elements, so we have two x's which are contenders, and we have the TET10 also. So why do I not want to use a TET10? Because it's bloody expensive. So if I go back to this slide, for the same size elements, similar accuracy, I expect to have 14 times as many nodes. So it's a much more expensive to solve model. The upside of that element is it's pretty easy to automatically TET mesh something. It's really hard to automatically mesh some. It's something that's really easy to X mesh, and then by all means do so. But a TET mesh is always easy to do. Okay, so if I compare them, so again, first the X8 and the X20, we've got the same kind of effect. So if I double the edge length for the X20 mesh, I'll have 8 times less elements. I'll end up with about half the number of nodes than I would have had for the X8. I'll get similar answers. I may actually need to mesh this slightly finer, so it'll probably be a bit more than that. For a perfect mesh, that's a very critical thing that I'll keep on mentioning. If I look at the TET4 and the TET10, TET4 versus X8 and TET10 versus X20 just doesn't make sense. It's more nodes than this and significantly less accurate. Again, a lot more nodes than this and significantly less accurate. If I compare these two with the same edge length, again, I'll get a very similar answer. But the advantage is, again, for this, I can easily mesh it. For these, I may have to spend quite a bit of time. Okay, so for any hex meshing or most hex meshing, we need some form of manual intervention to help break it up into more manageable sections that's extrudable to generate the hex meshes. Yes, I know there's a couple of supposedly newer methods that use a core of perfect hexes and then transition on the outside to either pyramid elements or TET elements. The problem with that is you can't mix first and second order elements easily. So we end up, if I have a X8 core, having to go to TET4s on the skin, and that's where the high stresses are. If I have a X20, I'll go to TET10. So I use this element because they're efficient, but now suddenly I need fine elements there. So effectively, it's not as great as it sounds, but it is a convenient in-between method than using purely TET10s. Or the extreme expense of, in some cases, meshing the X8 and the X20. So to make it a bit more clear, which element should you pick for solid elements? And the answer is it depends on your model. For small models, TET mesh is not that expensive. I mean, if a hex mesh runs in 10 seconds and a TET mesh runs in 2 minutes, I don't care. If that's the only model I need to run, it's probably it's going to take me longer to set up that model than it is to run. So in that case, it doesn't matter which one you run. As the model becomes larger, you get to the point where the time it takes to solve becomes more significant. But in most cases, for linear analysis, you don't ever get to the break-even point unless it's a very simple geometry that's easily X-meshable. To put it into perspective, it's pretty easy to TET mesh a really complex part in 5 minutes or less, and that same component can take you a couple of days to X mesh in certain bad circumstances. So if that TET mesh doesn't run at least 2 days, you haven't scored any time by solving it and breaking it up into X's. So the same goes linear analysis. It favors TET meshes simply because it's a single analysis that we need to perform. For nonlinear analysis, there's a complication. Every iteration that it performs is a linear analysis on its own. So that multiplies the cost of that solving time. So an example would be, let's say I have a model that takes 1 minute to solve linearly. Non-linearly, every iteration will take a minute. If I have 1,000 iterations, that's 1,000 minutes, which is something like 14 or something hours compared to a minute for the linear analysis. So in these cases, we try and rather get an efficient X mesh than a TET mesh. So putting that into perspective again, and let's assume that coefficient was, or the exponent was 1. So for the same mesh size, X's and TEDs would run at least 14 times slower. So the X mesh non-linearly ran in a day, the TED mesh would probably run in 2 weeks. I can make the same argument for memory usage. For the memory usage, the TED mesh will have at least 14 times the memory requirement for the same edge length. Okay, now again, it's more complex because we don't mesh a complete model with the same edge length everywhere, but hopefully you get the picture. Okay, then another one is, which I've already briefly mentioned, is now and then we get something it's just easy to X mesh. In that case, why do you need to TED mesh? So even if it runs in a couple of minutes, if it's about the same effort to X mesh and TED mesh, there's not much reason to use the TED mesh. Okay, so getting back to second order elements, we haven't discussed them in much detail. I'll have an additional section that explain a bit more about how they behave, and especially compared to first order elements. But if I compare quad 4 and quad 8, or X8 and X20, or a try 3 and a try 6, that second order element is significantly better and they perform really well compared to the first order elements. In most cases, except the try, and the TED, which first order TEDs and tries are really bad. About doubling the size of the second order element is similar to the first order element. So you end up with a lot less elements and slightly less nodes. There's unfortunately a but when you look at second order elements, and it's a long one. Okay, so second order elements is very sensitive to mid-node distortion. So if you take that mid-node and you move it normal to the edge or normal to the face, effectively we're generating a parabolic face, which we can nicely approximate the circular section, for example, with. The downside to that is we're moving the integration points closer to the surface, and we get to the point where some of those integration points may actually lie outside of that face. So I'll show you later some examples of that. And it's really easy to get that kind of elements in a model. What that means is that element cannot be solved, period. The solver will just stop. It's not a really bad element, it's an impossible element. So we, in that case, have to try and remesh a bit to get to the point where none of the elements are inside out, at least. Okay, so if I take an element on a fillet, for example, and I take that mid-node and I move it on the radius, I get a much better representation of the geometric properties of the part. That's the upside, so I better represent the reality in terms of volume of the element. The downside is the element degrades in accuracy, which means it's a toss-up whether it's actually more accurate to move it or to simply leave it halfway in between. I'll show you some examples later what I mean by that. It's easier to visualize. The second one, and again I'll show this later on, we have an uneven force distribution for constant pressure on second order elements. What that means is if I take a single second order element and I apply a constant 1 MPa pressure on one face and I request the applied forces, bear in mind the finite elements solve on the node level, so it has to be converted to a force. So depending on the element, you can get to the point where the coordinates show a tensile force and the mid-node is a compressive force. That is actually the case in Mark for the TED10. I'm not certain whether Nastran's TED10 formulation is the same, but it will have a very similar kind of response. Even the X8 will have very small compressive forces on the corner nodes and very large compressive forces in the mid nodes. So visually you see there's a really weird force distribution while actually it's a constant stress. Now that automatically means it's not compatible with first order elements. I cannot connect two first order elements to one second order element and expect reasonable answers, because the relative stiffness between those nodes just does not tie up. Physically, it's possible, solvers will allow it, but you will see a really, really weird stress distribution on that interface. Okay, then an additional complication that comes from the previous one is that we cannot use a contact algorithm that's based on forces. What I mean by that is contact says if a node is in compression, there's a compressive force, it should stay in contact. If the tensile force, it should release. But if I look at that previous example, some elements will actually have a tensile force, even if it's a compressive stress at that location. So that's especially true of T10s, but even X8s, the moment you have a slightly uneven compressive stress, we still get to tensile forces at corners. So we cannot use it. We have to use a pressure-based or a stress-based contact algorithm, which is more prone to issues. It's a good method instead of a great method, or a great method instead of an awesome method. Another one is there's a difference between the stiffness of the corner nodes and the mid nodes. So in theory, that's not an issue, but we get certain models where it actually becomes an issue. If I run a model that's got something like rubber in some regions and steel in others, we get to the point where the solver at some point says this model is badly constrained. Actually, what it says is not it's badly constrained. It simply says round of error is becoming significant. And that's especially true the finer you mesh. So if I have a steel and a rubber part in one model, I'm more likely to have issues if it's second order elements than I'll have with first order elements, simply because I've got much less variation in stiffness between there is no mid nodes and corner nodes to worry about for these kinds of elements. Okay, so when we run into this kind of an issue, that round of error is not propagated and you get a weird answer. The solver simply stops and says, sorry, badly constrained. Okay, so just to show you some of the effects of distortion and compare first order and second order elements, we look at this model, a simple plate with a small leash, not a really small hole, and I apply a load to this. In this case, I'll mesh with a reasonably constant size element instead of meshing coarser everywhere else. And there's a reason for that. Often we have plates with hundreds or even thousands of small holes, and it's much easier to, instead of breaking all of these regions out and providing a better mesh there, we simply mesh everything with a small mesh. Again, back to the time it takes to set up the model. Okay, so what I'll do is I'm splitting it as a symmetry model like this, and that section there, apply exactly the same load, but the one on the left will be a first order mesh, the one on the right will be a second order mesh. Okay, so the first one, I used a mesh size that for that radius that was there, only have a single element across this. So on the left-hand side, first order elements, it's a straight line, and there's not enough information to even approximate that radius better than this. On this one, that mid node is moved. It's shown as straight lines because it's a visual effect. In the background, it is this parabolic distribution. However, I can already see that element is pretty badly distorted. Is that mid node there has done something pretty bad. Even so, this model, you can see the stress predicted there is a bit better than there. But bear in mind, it's got a lot more nodes than this one as well. Okay, so if I look at this, so this is the X component of stress, X being horizontal. In this case, the bottom one is one element, that one is two elements in the radius, and the quad 4 has 2 nodes or 3 nodes there, and this one has 3 nodes or 5 nodes in that region. So you should already see it's not quite fair to compare these two directly like this. It's better to compare effectively something like this, where we have at least on that radius the same number of nodes. Okay, fair is fair. This model will also have slightly more nodes than this one. We'll actually see later on. What's interesting in this one is just visually looking at these two, I can already say that this answer makes more sense than this one. Firstly, that stress is higher than at that location. It's not too clear in this picture. I'll show you the numbers later on. But another one is, if I look at the stress patterns, it's relatively smooth. If I look at this one, it's still relatively jagged. So I'm not so certain this makes sense, but it's a decent answer instead of a great answer. Okay, if I now go to, so this is again the previous top image, and that's again one finer, so it's 2 and 3. In this case, this is 5 nodes and 7 nodes. This is 3 nodes and 4 nodes. If I look at the stresses now, this one is definitely better than this, and this one and that one is similar, although this one is probably a bit better. We'll see how the nodes compare in a bit. And I do the same, even finer. What may not be obvious is the scale keeps on changing, which is why the stress pattern changes fraction. And then on the finest mesh, we get this kind of result. Okay, and extract the results. On the quad 4 model, so the left, and the quad 8 model on the right, if I had one element there, I predicted a maximum of 158 MPa stress in that corner. 158 nodes in that mesh. So 120, this one predicted 176, but it's not surprising because we have a lot more nodes and it's a higher order mesh. So it's not quite fair. If I look at this one, so that one had 3 nodes in that corner, that has 3. Now the first order mesh is actually significantly better than that one. So if I go back to the first one, that answer was 205, and that was, what is it, 176 or something. Okay, so in other words, slightly more nodes, but significantly more accurate. And that gets back to my argument about this element being, even if there's enough nodes in theory to capture it, that element is just plainly too distorted. As you mesh finer and finer, that becomes less important. So these, even if it's on the radius, that element is not nearly as distorted. So as you mesh finer, the second order element actually becomes better quickly. But for coarser meshes, it's not quite the case. Okay, so if I then go to 5 nodes in the radius, and I compare it there to 5 nodes, 255, 255. Number of nodes, 1760, 1566. So in other words, in this model, except for the first really coarse mesh, the quad 8 model is slightly better than the quad 4 model, if I have the same number of nodes in that radius. Because they've got very similar accuracy answer, but we have slightly less nodes in this case. So in this case, it effectively tells you that whether it's a quad 4 or quad 8 model, we'll get for the same number of nodes very similar answer. As the mesh grows finer, the quad 8 becomes progressively slightly ahead, except we're kind of converging to a stress level there. So maybe 275 or something, probably not even as high. And every further refinement simply gets us slightly closer. So we get from a 5% error to a 3% or whatever. So effectively that becomes less and less of an issue as we mesh finer. Okay, so that said, if I take this in conjunction with this slide that says second order elements as issues, that's the distortion issue. If I want to run contact models, then in that case, it probably makes more sense to run the first order model because I'll have less issues with contact and will probably converge faster and slightly more accurately than the second order mesh for the same accuracy answer. But again, it's entirely up to you which one makes the most sense. Once we get to thermal analysis, it becomes a lot more painful. There's certain things that second order elements doesn't do that well if the implementation wasn't done really nicely. So, but that's a separate issue. Okay, so back to what we discussed in this session. We talked a little bit about the order of elements, but more the effect of the accuracy and computational cost than exactly why, and we briefly started on distortion. every element type has got a different type of distortion it really doesn't like, and some types of distortion it's okay with. So that's some of the things that we'll discuss in upcoming sessions. Okay, so that brings us to the end of the session on meshing.